All right, so what we're looking at now is sections 2.1. And 2.1, we're getting into graphing. And the idea of graphing is we want to try to come up with a picture for what these relationships are that we find in mathematics. And we're going to talk about some of the foundations before we actually get into some graphing to go ahead. And the foundations are actually the relationships themselves. We're going to talk about something called a relation. Now, relations are essentially mathematical relationships, and they don't have to make sense. We can just say, think of it in terms of input and output. You have an input, it goes into the relation, and there's an output. And what we typically do is we gather the inputs and outputs as ordered pairs. Where the input is first and the output appears second. So for example, let's say we have 3, we put it into our relation, think of it as like a factory. We put in a 3, you get a 5. Now we don't know why we get 5, but we do. And then let's say we put in 4. And as an output, we get 6. All right, maybe we see how this is working. So if we put in 5, does that mean we get 7? And for some reason, who knows why, we get 1/2. Okay, fine, that's how the relation's doing things. At 3, you input 3, you get output 5. Input 4, the output is 6. Input 5, the output is 1/2. Who knows? But if we organize these as ordered pairs, we'll get 3, 5, input, output. 4, 6. And again, input, output. And then 5, 1/2, input, output, in this case. Now, what we talk about with relations is the domain and range. And what the domain is, it's the set of all possible inputs. And then we have the range. And this is the set of all possible outputs. So let's suppose that our relation R, it can only take 3, 4, and 5 as inputs, and that's it. You can't put in any other numbers. We're done. Well, then that would mean the domain for our relation R would just be the 3 possible inputs we were allowed. And because these are the only 3 inputs that are allowed, well, these will be the only 3 outputs we could get. So that means our range, domain and range, would be 5, 6 and a half. So let's take a look at another one of these. Now, let's say we have a relation that consists only of these ordered pairs. 1, 2, 3, 4, and 5, 5. And this is our relation, do kind of a cursive R for relation. And that's it. Only 1, 3, and 5 are the inputs. Only 2, 4, and 5 are the outputs. And there are no other mathematical relationships for this relation. That's it. So what's the domain? Well, again, the domain, it's the set of inputs. So inputs are always the first numbers in the ordered pairs. So 1, 3, and 5. And what about the range? Well, the range is the set of all possible outputs. Now, there isn't a lot of input-outputs for this relation, but it makes it manageable. But we have an output of 2, 4, and 5, the second number in the ordered pair. So that would be the domain, and that would be the range for this relation. Now, again, relations could be kind of random. Like, why was R in both of these two relations? Why was it giving a certain output for a certain input? And sometimes we don't know. There could be things you observe in nature, like let's say you're watching time go by, and your input's going to be time. And as time goes by, you're watching temperature change. Now, what exactly causes temperature change? Well, there's a kind of a big obvious one. You know, you see the morning, the sun appears, and then in the afternoon, it's high above, and it's really hot. And then when it's sinking, or when the sun is at sunset, things are cooling off again. And at night, there's no sun to be seen. It's cold or colder. So the sun has something to do with that. But there's other things too. There's wind currents. There's the presence of clouds. There's the tilting of the earth. And then if you really focus in on some random things, again, some of those wind currents come to mind. It can be very complicated to explain why at certain times of the day the temperature is exactly what it is. And this might be kind of complicated compared to, say, 100 feet away. Would you get a different temperature reading 100 feet away from where you're standing right now? What's making that temperature difference? Same time, just 100 feet away. So sometimes what causes the input to be paired with a certain output can actually be quite complicated. Now, most of the time, though, we're going to have some explanation, some procedure that takes the input, modifies it into an output. That's going to be more common, and we'll be looking at some of that. But before we get there, we want to talk about a special type of relation called a function. And functions actually have to do with time. To a certain degree, they have to do with time. They don't have to. Now, with functions, they are relations. And they're a type of relation with a special property, and it's this. No repeated domain values. It's a relation where no domain values are repeated. Now, it is okay to repeat range values. That's perfectly fine. But not domain. Now, what's going on here? Well, let's construct a relation that has to do with time, and let's say where you're located. So, I'm getting a little fanciful with this. But let's say at 7 a.m., you're at home. 8 a.m., you're at work. And let's say 12 p.m., Let's say you're going to go to Sonic. Get a burger, get some tater tots. 1 p.m., you're back at work. And 5 p.m., you're back home. Let's say you worked a little late, 6 p.m. So if we take a look at this, input is time. Output is location. So this relation, well, again, we'll call it cursive R again. It has a relationship between time and where you are located. Now, what's happening here is this is also a function. Now, we take a look, talk about domain and range, though. The domain are times. The range are locations. So in this case, if we were talking about domain and range, I'm going to kind of sidestep a little bit. We'll get back to functions. But here our domain is 7 a.m., 8 a.m., 12 p.m., 1 p.m., 6 p.m. And our range, now domain is the set of all the possible times that showed up in this relation. The range are all the possible locations, and really the locations, it's home, work, and Sonic. Again, with sets, we don't repeat the type of object. Sets just tell you the type of object. So this is a type 7 a.m., a type 12 p.m., type home, type work, type Sonic. So we just list the types once, and that's it. So that's our domain, and that's our range. Now, what makes this thing a function? Well, it's a function because no domain value is repeated. There's only one 7 a.m., one 8 a.m., one 12 p.m., one 1 p.m., one 6 p.m. Now, what would happen, though, if we did repeat a domain value? Like, let's say we had 6 p.m. Sonic. Let's say that was also part of the relation. Well, the problem with this is at 6 p.m., are you at home or are you at Sonic? Can you be in two places at the same time? And the answer is no. And so this is where time, in a way, really has an important role with functions. When we're recording something through time, especially if we're doing physics or mechanics, we're watching some point or mathematically, or maybe have an object physically that's hurling through space. And that object, outside of quantum mechanics, this object is, well, even with quantum mechanics, this object is going to be observed. So this will be true of quantum mechanics as well, as far as I know. My knowledge of quantum mechanics is not strong. This object will be observed in one place at one time. It can't be in two places at the same time. And what that means is that you have a situation here where you're at one time, you're in two different places. And this leads to what's called ambiguity in mathematics, where if you put in an input at 6 p.m., we're not sure where you're at. Ideally, a relation will say at 6 p.m., we know you're home. 6 p.m., we know you're at Sonic. But when you have both options available, we're not sure which one. Another one with time could be wages. Let's say you work for someone and they say, if you work 10 hours, we'll give you, say, $200. And then you talk to another manager and they say, if you work 10 hours, you'll get $150. And you're like, wait, what is it? If I input 10 hours of work, what's my output? Is it 200 or 150? That's ambiguity. functions remove ambiguity by saying whatever input you have, you only get one output. If you work 10 hours, you're going to get $200. There's no way you're going to get 150. At 6 p.m., you're going to be home. You're not going to be at Sonic. And so that's the idea of functions. And so the way we express this mathematically is we make sure that the input isn't repeated. If it's repeated, that means there's some other output that goes along with it. A repeated input means there's another output that goes along with it. That's not going to work. So no repeated inputs. That will guarantee there's only one output paired up with that input. So that's the idea of a function. So let's take a look at some of these. Let's say we have a relation like this. Well, let's take a look. What's the domain? Well, the inputs are only 3s or 4s. So type 3, type 4. In the range, well, we have a type 4. There's a repeat of a type 4. Type 5. Okay, so just 4s and 5s for the outputs. Now here's the question, is this a function? Now the outputs are repeated, but that's fine. You can repeat outputs. Again, we have repeated 4s for the outputs too. Where this isn't a function is we have repeated inputs. 3 to 4 or 3 to 5. 4 to 4 or 4 to 5. There's a drawing you can do called sort of a domain range chart. But here's our domain, and here's our range. The domain is 3 and 4, and then the range is 4 and 5. So let's say you work 3 hours, you get $400 bills. If you work 4 hours, you get $500 bills. So what this says, if I work 3 hours, I get $400 bills. But then this says if I work 3 hours, I get $500 bills. Ooh. Well, which is it? Am I going over here or going over here? That's ambiguity. Same thing with this. If I work 4 hours, okay, I get $400 bills. But then I could get $500 bills if I work 4 hours. Again, you don't know what you're going to get. So what this means, these repeated domain values mean we don't have a function. So let's take a look at another one. So again, let's look for domain and range. So the inputs are 4, 6, and 8. And the range, or the outputs, again, is that second number in the ordered pair, 5, 7, and 8. So now we've got domain and range. Now, here's another question is this a function? Well, there are no repeated domain values. Now, this doesn't mean a repeat. Just because you have a domain and a range of the same value, that's fine. You can do that. But amongst the domain values, there's only 1, 8, 1, 6, and 1, 4. And so if we were to do a domain and range chart or domain and range graph for 6, 8, and we have 5, 7, 8, what we're going to see, you know what happens if you work 4 hours, you get $500 bills. If you work 6 hours, you know you're going to get $700 bills. If you work 8 hours, you get 8 $100 bills. So you know what you're going to get. And that means this is a function. There's no ambiguity. One more. So again, let's look for domain and range. So domain, it's all the inputs. So we have 4, 5, and 6, all the types of inputs. And then for range, what we're looking for is, well, what's the type of output? There's only one type of output, and that's the number 1. All right. So is this a function? Well, it is. Yes, the range values are repeated, but that's okay. The domain, they're not repeated. So if you do your domain range chart, well, you work 4 hours, you'll get a $100 bill. If you work 5 hours, you'll get a $100 bill. If you work 6 hours, you will get a $100 bill. So you might not like how that's set up, fair enough, but you do know what you're going to get. 4 hours or 5 hours or 6 hours, you know you're going to get that $100 bill. And that's the idea. This is still a function. All right. So we like to express functions in a special sort of way. You see me use this cursive R for a relation. We tend to express functions with their own special notation. So you've seen stuff like this, like y equals x squared minus 2x plus 1. See something like this, quadratic equation. We can express this in what's called function notation. And this is where you get f of x equals x squared minus 2x plus 1. So the difference between the two, there's not too much. Like for this one, we might say, let x equal 4. To find out what happens when we let x be 4, we'll get a value for y. So for this one, what we'll do, instead of saying let x be 4, we'll simply say f of 4, and then replace all the x's with 4s. 4 squared minus 2 times 4 plus 1, or 16 minus 8 plus 1, and that gives you 9. So what you might see is, instead of x, y, you might see x, f of x, which is 4, 9. And so that's what that f of x notation is. Now, what we typically do with functions, we can still use y, as we're not prevented from using it. So y, we'll go back to our x squared minus 2x plus 1. And again, this is just some terminology. X, again, is our input. And the thing about the input is we get to freely choose it. Now, there are some inputs that actually aren't allowed for some functions, like inputs that cause division by 0, square roots of negative numbers, logarithms of numbers that are 0 or less, things like that. We want to not use those numbers in those kinds of situations. But generally, of the numbers that we can choose from, we can just choose them however we feel like. So we refer to the input, or x, as the independent variable. Now the output y, and we could also refer to this as f of x. But the output y, that is something that is dependent upon what we chose as input. So that means y is what we call a dependent variable. Its value depends upon the value of the input. So one of the things that comes up is how to graph these functions. And we want to have a picture. We can sort of say that, well, what we're going to do, we have all these ordered pairs, and we say that a graph is worth, we say a picture is worth 1,000 words. We'll say in this case, a graph is worth 1,000 ordered pairs. And so we generate these ordered pairs using our, our x and our y, our inputs and our outputs, and then we plot those on our Cartesian plane. So basically what we're going to do, and this is a review, but let's say we have something like this. F of x is equal to x squared. So we'll choose some inputs, saying -2, -1, 0, 1, and 2. So what we get is f of -2, which will be -2 squared, and we're squaring the entire number, including the negative. We get 4. Or f of -1 will be -1 squared, again replacing all the x's with whatever went in between those parentheses in front of the f. And that's just 1. F of 0, 0 squared, 0. F of 1 is 1 squared, or 1. And f of 2 is 2 squared, or 4. So now we gather our ordered pairs. And so we get -2 and 4, -1 and 1, 0 and 0, 1 and 1, 2 and 4. So finally we graph these. So -2 and 4, -1 and 1, 0 and 0, 1 and 1, 2 and 4. So we connect going left to right. We have a point as we sweep to the right, here's the next one. Sweep to the right, here's the next one. Sweep to the right, here's the next one. Sweep to the right, and there's the next one. And so that gives you a rough picture of what's going on. But you can see there's sort of a general trend here. That helps us save time when we want to analyze what's going on with our data or analyze this particular mathematical relationship. So, one of the things we can do let me take a look here, is we can sometimes be given a graph and ask if that graph is a function. And one of the things to kind of keep in mind is a function does not have repeated x values. So in other words, we're going to get to something called the vertical line test. And what this says is, if you have a graph of some mathematical relationship, and if you can find any place on that graph where you can draw a vertical line through the graph, and it intersects the graph more than once, then you don't have a function. If a vertical line can intersect this graph more than once anywhere on the graph, this is not the graph of a function. Now, it could be the graph of, well, it's a graph of a relation, but not a function, not that special type of relation. So let me do some examples. So let's say we have this. And let's say we have a function like this, or a graph of something. And we have an x-axis, we have a y-axis that we could also call an f of x-axis. We could. Anyway, hopefully this isn't giving it away, but let's say we start drawing vertical lines. So intersects only once, intersects only once, intersects only once, only once, once. So if there's no place, you could try other places, there's no place on this graph where if you intersect the curve, you're going to intersect it at two places at the same time with a vertical line. It only works with a vertical line. So this means this is a function. Let's take a look at another one. So if we start putting vertical lines here, and that's okay, That's okay. That's okay. This one's a problem. Here we have a vertical line with two intersections. So this means this is not a function. Now, how does this relate to what we said before about repeated domain values? Because let's say this value is 3. Let's say this one is, we'll say it's also 3. And we'll call it 2. Let's call it 2. And this one, we'll call this 4. So what we've got, 0.32 and the 0.34. So in this relation, these would be two ordered pairs in this relation, and sure enough, you have repeated domain values. In this case, the 3 is repeated. So if you put in 3 hours of work, are you getting $400 bills or $200 bills? You don't know. This is ambiguous, and again, it's not a function. So another thing with graphs that you'll be asked to do, let's say you have a graph like this. Let's say you have something like this. And you're asked the question, several things. What's the domain? And what's the range? And then let's find f of 2. What's f of 2? Well, first off, the domain. Well, the domain is where along the x-axis this function exists. So if we take a look at it, it's starting at x is -3, and it's ending at x is 4. So this here would be the domain. Now let's look for the range. Let me grab some pins here. Well, for the range, it starts down here at -4. And then it's going, in a sense, along the y-axis all the way up until it stops at +4. So this is going to be the range. You can sort of say the function tries to cast a shadow onto the y-axis, and that shadow is your range. And then the domain, the function casts a shadow onto the x-axis, and that's going to be your domain. So the domain for this one It'll be -3, 4. And then the range for this function will be -4 and 4. Finally, what's f of 2? Well, what this means, when we have an x input of 2, what's the output? Now, the way we figure that out is we look to the graph. There's 2. Drop down here. So x is 2. We have a y value of -1. So that means f of 2 is -1. And so that's how you can find domain and range and find the values of functions on a Cartesian plane. Let's look at another one. You might know this, you might not. This is the top half of the circle. And if we were to graph this, we get something like this. So let's say we want to find the domain. Well, the domain is going to be the shadow of the circle on the x-axis. So as it casts its shadow downward, it's going to be this. That's going to be your domain. And it actually includes, they put some points here to include -1, 1. The domain is -1, 1. Now what about the range? Well, it could cast a shadow onto the y-axis like this or like that. So that gives us that. And so we get a range. And these points here are located at 0. So they'll cast a shadow onto y is 0. 0 go up to 1. The value does go up to 1 there. Now, is this a function? Well, this is the actual curve. And if you were to put vertical lines through it, they only intersect once. Again, this is the shadow part. So that's not part of the function here at all. And I'm kind of giving it away and calling it a function. So that's the domain shadow, range shadow. The actual function is here. And you only intersect it once with any vertical line. So it is a function. Finally, let's ask, what's f of 0? Well, here's x equals 0. And at x equals 0, this has a value of 1. So that's 0, 1, the ordered pair. So that means f of 0. Input 0, you get output of 1. And that's it. All right. So as a last example, I just want to play around with this function notation a little bit more. Let's see. So let's say we have this. So when we use function notation, we're just going to replace this x here with a number, and that means we replace all the other x's with that number. So h of 2. Well, this will become 2 to the 4th minus 2 squared plus 1, or 16 minus 4 plus 1, or 13. Or say we have h of negative 3. This will be negative 3 to the 4th minus negative 3 squared plus 1, or 81 minus 9 plus 1. So that would come out to 73. And that's just how you use that function notation. That's it. So if you have any questions about this section, let me know. Other than that, have a wonderful day.